Cool. Well, thanks for having me. Really excited by this year's speaker series. Excited by everything you guys do with, category theory, social systems, and so on. Luke and I actually published a paper a few years back on the evolution of music, so we know each other. But today I'll be talking a little bit about some theoretical work I've been doing, quantifying things like agency and social systems, and then showing you how I've been applying thoughts from that to some things in the history of thought. Uh, so we'll start with a quote. This is from St. Augustine in the 5th century, and he's describing methods of shipbuilding. He's actually talking about pagan gods, but he uses this analogy where he says, it's best that one vessel before being completed goes to the hands of many craftsmen, though one craftsman could have done it completely. But the thought is that is the only way to make provision for the multitude of workers, that individuals should learn quickly and easily just one part of the task, so that all will not have to become perfect craftsmen slowly and with difficulty. The idea being that in the context of shipbuilding, you have many people, some work on different parts of the ship, and with each person specializing on this coherent whole, what you get is a better shipbuilding process. And this mimics some of the things that Adam Smith discussed in the pin-making factory in the early eras of industrialization. And I think it's best put by the philosopher Michael Polanyi, who says, what we have to imagine is that we're given pieces of a very large jigsaw puzzle. Suppose that for some reason, it's important that our puzzle be put together in the shortest time possible. We would naturally try to speed this up by engaging a number of helpers, but the question is, in what manner could those helpers best be employed? And this is kind of a good definition of what I study, which is collective problem solving, where I examine how structure influences collective decision making, collective processes, and different kinds of outcomes. Methodologically, to do this, oftentimes we use network science, such as with these spider monkey networks I've been working with. You can generate random graphs. You can generate all kinds of bespoke other forms of graphs, like this connected caveman in the bottom left. Originally, the field started with experiments, combining networks with experiments. So here's a paper by Simon and Gutzkow, where what they did was they had people had different kinds of cards, and what they had to do is they had to figure out what card was missing from the group that they had. So you have like a square card, a triangle card, a circle card. As you transmit through these networks that they did by creating these cardboard partitionings, what you figure out is what's missing from our group, or what is it that I have that the rest of the people don't have. And that's easy to do at a small scale, but as you tend to scale things up, it kind of gets hard to simulate a society or larger social unit. And so we rely on agent-based models. And I view my work combining network science and agent-based models as doing what Michael Polanyi said, in which the agent-based models specify the puzzle and your puzzle solvers, and your networks, by introducing some kind of structure, tells you in what manner these solvers can best be employed. Most of these models, in the agent-based modeling context, you can do this a lot of different ways. One of the most popular one is the NK landscape model, where you have n bits. You align the bits in a specific sequence, and you get some kind of score. And you have another parameter, k, which basically notes the interdependencies between those bits in the score, such that the position of one bit and that score is dependent on another bit next to it. And what you can do is you can increase k to n-1 value. And what that does is that gives you a very rugged fitness landscape, where as you try to change or you try to find local minima or local maximum on these landscapes, it becomes very complex. You also have what are called multi-arm bandit tasks, where an agent tries to draw from some kind of a resource. Every once in a while, they get a good payout. Every once in a while, they don't get any payout at all. And they're trying to figure out which is the best bandit, the best slot machine, per se, that they should be drawing from. And then there's more bespoke ones, like the potions model that I'll get into later. But all of these are more or less pretty much the same model. You have some kind of fitness landscape, and the agents are traversing it, trying to find the best or most optimal solutions. These are based off of Sewell Wright's idea of the gene fitness landscape. This is from a talk that I attended at the Santa Fe Institute, where they were just going through the history of complex systems and complexity science. And in the background, I thought it was really fitting that they had the figure from Wright's paper in 1932. So for Wright, what he was trying to map out is how is it that a biological population can find adaptive peaks on a landscape, say when you're at a suboptimal peak, how do you get to a higher peak? What kinds of population structures will allow you to move from one peak to the other? Does structure matter at all? Is it simply you just need a really large population and you'll get some level of mutation? Or is it that you need migration between different subcomponents in the population? And this has a wide number of extensions. So you see Wright's model going all over the place. It has kind of a history in gradient optimization. There's a connection between him and Haskell-Curry. When Haskell-Curry was trying to solve some of the equations for gradient descent for shooting down Japanese Zeros in World War II, has applications to political economy through F.A. Hayek, genetic algorithms through John Holland, collective problem solving through Stuart Kauffman, and many, many others. But one gripe I have about these models, and in particular, oftentimes with my own work actually, is that we tend to present the results which happen on a collective level and happen to be about collectives on this kind of population level. Going back to the fact that these models come from population genetics, what we're generally talking about are these collective outcomes rather than what's happening processually within individuals in the population. And so to understand what's happening at the large scale, we tend to ignore the properties of the small. And oftentimes, these models are what are called phenomenological models. They're models of what things are doing when they're doing them, typified by folks like Ludwig Boltzmann in the early 20th century, who realized we could develop a new kind of physics, statistical mechanics, by ignoring the particular, which has the same root as the term particle, in favor of just viewing macroscopic properties and ignoring what the individual particles are doing themselves, which is not bad, and also not surprising given that what we're talking about is collective intelligence. But something that I often see is that we shy away from mechanism when we're discussing these outcomes. We often use general principles. We talk about causal language, but we do not have causal explanations. So we say, oh, transient diversity is a general principle. Different kinds of networks allow for different kinds of exploration on landscapes. Here's a very egregious example, says this kind of network arrangement allows for shielding of periphery nodes. They never show this in the paper. It's my paper. And my idea is that what we have to do is we have to fix that. So what are we missing on the unit level when we conduct this kind of chunking? In addition to the things that we've done using this complex systems approach, I'm trying to ask, how do we go from a model of what is happening to why is it happening? And so today, I'm going to be talking about some of my work and how I've been reframing it, asking how is it that the individual agents within these collective systems are actually yielding these better collective processes. And so the examples I'll use are one of a agent-based model I use to model science and scientific progress over time, and one in philosophy. And if you think about it, these sound like two different things. In the context of science, what we'll be doing is we'll be asking, how is it that agents in some complex landscape can find the correct solution or the maximum in their landscape? And in philosophy, which has a different kind of problem, we'll be asking, how is it that their social networks can be structured such that they have a productive discourse rather than a non-productive one? So we just brought up Newton. We'll talk about him again. Very famous guy. And at some point he said, if I've seen further, it is by standing on the shoulders of giants. Apparently, he was mocking when he said this, and also it's a very old quote. But it's not a trivial question because even though Newton is saying my community has yielded a lot for me, he was a very important guy, right? He described calculus, the laws of motion, universal gravitation. He invented the telescope. He was, by all means, kind of an extraordinary figure. In the context of communities, we should ask, what are the mechanisms or supposed mechanisms for enabling better systems of collective innovation or better problem solving? And one we came up in our lab a few years ago was this concept of transient diversity. And the idea is that if you have a population and you give it the ability to maintain a diversity of solutions to a problem, everyone's thinking about different things, but nevertheless, they can still communicate with each other. You'll end up having more diversity of ideas, and this diversity of ideas will lead to better outcomes. And many different mechanisms can basically yield more diversity. So you can have more sparse networks, people are talking to each other less. You can simply give them different kinds of search strategies. This is like the work by Scott Page. You can simply slow down the speed of interactions such that they're not talking to each other all the time and do all kinds of other things. To drive this point a little bit more closely, this is similar, basically the same idea as Fisher's fundamental theorem of natural selection, which states that the strength of selection in a population on a trait, or at least its rate of change, is related to the amount of variance of that trait. So we effectively just reworded this for network science. But overall, I became very dissatisfied with this because it came close to us as presenting a free lunches theorem. Just keep introducing diversity, nothing bad will ever happen. This is just what you have to do all the time for all kinds of problem sets. This was also part of the debate between Sewell Wright and R.A. Fisher back in the 1940s and 1950s, where they had a disagreement about similar things. And so you can think about the work that I'm presenting as more or less recouching some older ideas in a network science context. So this diversity, as we know, is great for the networks and collective problem solving and their outcomes. But can we ask about what's happening on the agent level? Are there actually endogenous costs to increasing diversity in a system? Or is it the case that innovation is simply a free lunches theorem and you should just apply it in all contexts all the time? So I built an agent-based model based on this experiment from 2016 by Maxime Derricks and Robert Boyd called the potions task, where basically what groups have to do is they start with the same set of ingredients. Each person has 6 ingredients, 6 potions at the beginning of the experiment. Those are the ones on the bottom. And what they do is they combine these potions to try and figure out new ones. So you see if you combine the orange beaker, the red orb and the yellow orb, you get this kind of purple flask. And then you can use those new potions to combine and find other ones. And their treatment was really brilliant. So what they did was they had a group of 6 people where everyone could see the solutions of everyone else in their group. And then they had groups where you had 2 people and they could only see the solution of their partner. But every 5 steps or so, every 5 iterations of making these mixes, whether they failed or whether they succeeded, they could look over at another group and see what they had come up with. And their question was, which groups are going to discover the best innovation for this A path or this B path, because there's path dependency in the model. If you discover this purple potion at the beginning, you're less likely to discover this orange one just because humans have a recency bias when they think these things through. But the other thing is if you discover both of the terminal potions on the A trajectory and on the B trajectory, you can combine those 2 potions together, and that basically ends the experiment, says you want it, and everything's done. And what they found is that these fully connected groups were never able to find this final potion, while these partially connected groups, the groups of 2 that could see what the other ones were doing, did it about 60% of the time. So this was kind of an experiment showing this diversity theorem in the context of some kind of innovation task. So we turn this into an agent-based model. What you do is you initialize some kind of graph or network with your agents on it. There's a random graph, which we'll hear about in a little bit, a connected caveman network, spider monkeys, and the agents start with an inventory, just like in the experiment. At each time step, an agent on the network will look at its neighbors. It will select one of its neighbors at random. And what they'll do is they'll exchange potions with each other. So they'll say, okay, I have 2 potions. Let's exchange 1 potion with you and see what we get. If they end up finding a potion, they keep it, and they can use it in subsequent connections. But the thing is that we've given the agents a bias for novelty. So if you look at the center here, each of the potions are scored by some value. So their probability of selecting a potion when they make a trade, when they're trading with another person and they say, okay, I want to give you this and we'll combine it with this, is dependent on this score that the potions have. And you can set it based on these scores here, 48, 109, 188, 358, or you could set it 1, 2, 3, 4, and you get the same results. And this creates path dependence in the model. Because say they start up the age trajectory, they're just going to keep using the new potions they have there, and it's unlikely they're going to go back to that initial set at the bottom and find a potion on the B trajectory. So if they combine their items and they get the right potion, what they do is they diffuse it to their neighbors with some set probability. So if that probability is at 0.5, 50% of their neighbors will get the potion, 50% won't. And the simulation ends basically when they discover this final potion or after 1,000 steps. And so for our measures, what we looked at inequality using a Gini coefficient based off of their scores because their potions are scored. So maybe you have a population where everyone has a similar score, in which case the Gini will be low, the inequality is low. Or if you have one person who's hoarding all the really good potions and everyone else is poor, your Gini coefficient is going to be very high. And in terms of performance, what we looked at the steps to this crossover. The crossover is when you find this terminal potion. And so populations are thought to be really high in performance when they complete the task quickly, and low when it takes them a very long time. So the first thing I looked at were population size and the connectivity of these networks. So what you see here is on the y-axis is the time until this final potion is discovered. So lower values are better. And on the x-axis is the edge probability for a random network. So a fully connected network has an edge probability of 1 and an edge probability of 0.5. About half the nodes that could be connected in the network are connected. So if you have a 100 agent network and the edge probability is 0.5, on average, your degree or the number of neighbors that each agent has is going to be 50. For 10, it's going to be 5. And what we find here is that large populations innovate faster. You see that this yellow curve is on the bottom, this purple curve is on the top, and then there are intermediate values for population sizes in between. And also, less connected networks tend to innovate faster because what they're doing is they're slowing down these rates of interaction. Individuals are able to hold on to their solutions without necessarily having the same ideas as everyone else. You can think about it in a fully connected network. What's happening is it's almost as acting as if there's just one node. Everyone has the same information. They're going to use the same potions all the time. But if you split the population up a little bit, what ends up happening is you get more diversity of solutions, more diverse potions to combine. Now, that was performance, but if you look at inequality, you get the exact opposite effect, and it's almost proportional. It's almost as if you took this curve and you just inverted it, where what you find is that larger populations, which in this case is the dark line rather than the yellow line, are less equal, and less connected populations are also less equal. And so there seems to be this trade-off between performance and inequality in these systems. The other thing is that the way that this was analyzed is, with regards to population size, is at each step of the simulation, all of the agents kind of go at once. So there'll be 100 combinations at each step for a population size of 100 and 10 for a size of 10. But if you just look at the sheer number of total potion combinations, So how many times that individuals make successful swaps in the population. You get the scale-free behavior. It's basically you have to find the same number of combinations to complete the task, whether you have 10 individuals or 1,000 individuals. It takes the same amount of work per capita within populations of different sizes. Yet their performance is the same. So that says something about some of the arguments you oftentimes see about population size and cultural innovation. Folks like Matt Iglesias or many others say, if we just increase the number of people, things will be great. But actually, it turns out that you could do the same amount of work with smaller populations. It might just take more time, and you might need some kind of different network structure. And what's really weird about this too is that the edge probability is held consistent. So this is not network connectivity. It's not some measurement of the average degree in the network. So again, at a 0.5 with 100 agents, on average, agents will have 50 neighbors. But with 10, it'll be 5. And yet, for whatever reason, these are radically different networks in terms of their average degree. It still takes the same amount of work. The other thing you can look at is information diffusion. So I mentioned earlier that populations or agents have the likelihood of transmitting their successful potions to their neighbors with some probability. And what you find is that when agents are greedy and they don't share, that actually increases their capacity to innovate. You can think about this in a societal context in things like patents, for example. That gives you kind of a first mover advantage and forces other individuals to innovate around you in a space rather than giving everyone the exact same things. But it also, again, proportionally increases inequality, although with this steep drop off, this transition at lower diffusion probabilities than at higher, which says, even though you're going to get inequality out of a system, there might be a way to decrease the inequality per step while basically maintaining levels of performance. So there's different ways that inequality interacts with this idea of transient diversity. You can also do this with real-world networks. So these are the hunter-gatherer networks from another paper that used these this potions task. These are Octa hunter-gatherers from the Philippines. What they did was they followed them around. They had transceivers on their wrists so they could see whenever they talked to another individual. And they just built those social networks up and then did the same task. Here's a chimpanzee group, a social unit. They do really bad at the task. I like this example because it says that, even if chimps had the same cognitive capacities as humans, something about their social networks might inhibit them from doing the same kinds of cultural behaviors that we have, particularly in light of things like cumulative cultural evolution, which Luke talked about. There's professional networks. This is a big one from Network Sciences, Zachary's Karate Club. And then there's this really weird network, which was my PhD department. And so far, that's actually the best network I've found for completing this task. But what you see here is that several of these networks have populations of the same size. So these coastal hunter-gatherers have a population that's the same size as the Karate Club. The forest hunter-gatherers have a population size that's the same size as my academic department. But their outcomes are radically different, which tells you that there's a lot more going on than population size when it comes to innovation. So what is it about certain populations that allow them to do better than others? So this is just an example run from the simulation. So on the left, you see a number of colors. The dark blue means that the agent still has that initial set of potions. At yellow, it's kind of gone up to the first tier. At green, it's gone up to the second tier. And at light blue, it's at the terminal tier of either the A trajectory or the B trajectory. So you run it some steps forward. What you see here is that a lot of the agents are stuck at light blue. They're either at the top of the A trajectory or the B trajectory. But what you see is that there are some basically laggard agents who are lagging behind in the system. They're not actually advancing as far as the other agents. But when you see where the transitions take place in the system, who actually discovers this kind of final potion? These laggard agents tend to be really critical for pushing the system over the edge, what I call the loser node phenomenon, which is where you see these nodes, it doesn't seem like they are performing as well as the rest of the individuals in the population. But actually, what's happening is they are producing second order effects for innovation by remaining behind from the rest of the population. So basically, you need these outliers in order to advance. My colleague at the Army Research Labs and I tried to isolate this effect using a stochastic block model, where what you can do is you set up a probability matrix. You come up with two communities, A and C. You set parameter A, which is how connected A is connected to itself, C, which is how connected C is to itself, and then B is how connected they are to each other. And you can produce different kinds of network structures to basically increase the number of these loser nodes in a system. So here's an affinity network. It's where A and C are well connected to each other, but they're not very well connected. Sorry, they're well connected to themselves, but they're not very well connected to each other. So you could think about this like the hemispheres of the brain, where you have a left and right hemisphere, or even your fists if you just hold them up. We have a centralized core periphery network where A is very connected to itself. It's very connected to C, but C is kind of a sparse network. They're not really connected to each other. We call these centralized core periphery networks. And then the one that maximizes loser nodes are these decentralized core periphery networks, where A is this tight cluster. They're all kind of hanging together, but C is comprised of nodes which are neither connected to each other very well, nor connected to this kind of central reservoir. And what you find in terms of the results is we use this theta parameter where you can run this simulation that you just saw. As you increase theta, going from a decentralized core periphery network to an affinity network, it will turn the networks from decentralized core periphery into an affinity network. And what you find here is that the decentralized core periphery networks do much better than the affinity networks, than the modular networks. And conversely, these affinity networks do better than these centralized core periphery networks. So oftentimes what you hear is what you need population structure, you need fragmentation. If you have two groups, that's really good. But also what matters is the intrapopulation structure in light of performance. And what I liked about this study is that our most extreme comparison of these decentralized core periphery networks has been noted elsewhere, not just simply in light of these agent-based models. So, for example, Danny Bassett and their group, along with Mason Porter at UCLA, found that as you're learning a new task, you can basically map out how different areas of the brain are talking to each other. And what you want is, say you're learning the piano, right? You want to be able to preserve your core competencies for your basic piano playing skills while innovating around the edges. So as you're adding new tasks, you're trying to learn some kind of new movement in jazz. What happens is your brain restructures, or at least the activity is structured such that you get these core periphery networks where something is holding this core competency while the exploration is happening at the regions of the network in this periphery. This was also noted by Ernst Mayr, who said that, if you're going to divide a genetic population in some idealized manner, what you're going to want is you're going to want to have some kind of centralized population which can take novel mutations and fixate them, but you want peripheral populations which can kind of innovate around the edges. They can drift a lot more. So you want population drift in some parts of the structure and fixation in others. And he talked about it in terms of peripheral population, similar to what we found in our study and what Danny Bassett talks about in the human brain. So going back to these findings on inequality, a core question is who's driving it? So what we did is we took different centrality measures of all the nodes in a network. Degree centrality just says who has the most neighbors. Betweenness says how many paths between distant nodes have you basically at the intersection? And then closeness says, basically, in terms of your furthest path from other people in the network, who has the lowest furthest paths. So what this plot shows is, this is for degree centrality. On the x-axis are different findings by the agents. So the A potion and the B potion. So for A and B, that says I found the best potion in the A trajectory. B says I found the best potion in the B trajectory. None means I found neither of the best potions. But final is the one to pay attention to. This is the one that ends the simulation. And in these cases, for each type of centrality, what you find is that for finding the final potion, it's the most central agents who tend to do it, while the rest, even for the A and B trajectory, tend to be unremarkable. So they're higher in centrality while the others really are not. And that indicates that who's driving the inequality tends to be the central agents. What they're doing is they're serving as ties between disparate communities in the network, what we'd call broker effects in economics. You think about Israel Kirzner and others who discussed, what does it mean to be an entrepreneur? And from a social network perspective, oftentimes it means being able to connect two communities that weren't really talking before. But altogether, across all model parameters and all networks, what we find is an inverse relationship between performance and the number of steps and inequality. So on the y-axis is your performance, on the x-axis is the inequality, and what you find is this kind of linear, curvilinear relationship where as you increase in performance, you see Merced all the way on the bottom, you increase in your inequality. And this just seems to be a fundamental trade-off. It's not something that you can get out of. This is all possible parameters in the model, and nevertheless, what you end up with is this curve stating that more or less the flip side of diversity, as it enables your performance, is going to be inequality. So overall, we find four things relevant to the structure of innovation. First is that less connected networks outperform more connected ones, which many people already knew. We find that peripheral agents increase group level performance, and that the agents which are driving the inequality tend to be more central, but that across all networks, across all parameters, and across all means for improving collective problem solving, from diffusion to network connectivity, what we find is a proportional increase in inequality with diversity. So what does all this mean? First, we can talk about inequality. This is not inequality in the economic sense, although it could kind of create it. But instead, it's an inequality of good solutions in a population where less equal networks have very few high-performing agents. In other words, what we're getting is we're getting genius effects among otherwise completely dumb agents. All the agents have the exact same heuristics. They have the exact same capacities. They don't have different rule sets. What's happening is they're privileged by their positions in their network. So not to say that Isaac Newton was not hyper brilliant, of course he was, but part of what may have driven his success is where he was situated in his broader social sphere. The second point is about second order effects. What we found is that these peripheral networks tend to increase the performance of the whole system, but they're not the ones getting the highest payoffs. The ones getting the highest payoff are the ones that are kind of in the center, making these kinds of final connections. And so when you're looking at capacities for increasing your innovation, it might mean that these loser nodes who don't get as much credit, these kind of renegades in scientific systems, for example, are going to increase system performance without getting the same kind of accreditation. And then finally, with light of this free lunches theorem, there's this brilliant book by Joel Mokyr where he's talking about innovation and its relationship to economic progress. And he says that all work on economic growth recognizes a residual that cannot be explained by more capital or more labor. And he says this must, to some extent, be regarded as a free lunch. He says that technological change, or you could say innovation, is what produces this residual. That if you get more innovation, basically you have this free lunch. But our argument then would be perhaps it's a free lunch in some that it's not an endogenous free lunch, that your costs actually are in the system and they're borne by inequality. Whatever measures that you have which increase the innovation in the system in light of diversity, things like patents, things like competition and so on, population structuring, produce inequality, and that's an endogenous cost to the system. All right, so that was it for the theoretical portion. We'll talk about some empirical findings. So this is the network you saw of Isaac Newton. And what you see is that many of the people embedded with Newton are not merely scientists, but also represent kind of an epistemic system of a different name, which is philosophy. And in this project, what I wanted to ask is if we can assess different systems of philosophy in terms of their network structure and their levels of productivity or liveliness of their discourse. So this has been kind of an important perspective in the so-called science of science, which since this paper in 2018 has kind of founded itself as its own field. There's been an explosion of all kinds of different studies, things from my lab, different advisors, people I've worked with. And what we have to ask is, are these rules for science true for all intellectual systems? So when I'm discussing philosophy, I'm discussing something that's very broad, things ranging from the origins of mathematical logic to theological discussions, or what was happening in Baghdad during their golden era of the Arabic world. And when thinking about progress and productivity, in science, you can look at a few different things. In the science of science, the most popular one is looking at citation counts, but you can also look at real world outcomes. You can say, does this funding schema or this grant system, as you increase money in this, do you end up getting fewer heart attacks over time and things like that? But for philosophy or systems like philosophy, the answer is less clear. What would progress look like in these sorts of systems? I like the perspective of Richard Rorty, who says, the point of philosophy should not be like the purpose of science. It's not that they're trying to solve problems, but actually that philosophy as a collective enterprise has a kind of end goal or telos of just keeping its conversation always rolling. You could think about it like a strange attractor. Philosophy is a system of conversation that is just trying to propagate itself through time. Cardinal John Henry Newman, in his book on tradition, basically argued that, well, science is not special and neither is philosophy. Some of the rules that apply to philosophy should also apply to science, but should apply to all kinds of different discourses. So in his book, Tackling the Problem, Randall Collins wrote this book, The Sociology of Philosophies, in 1998, where he argued that productive errors in philosophy are driven by the structure of social networks, similar in science, but specifically that productive networks have these centralizers who funnel energy to their pupils. You get this really exciting person who says, this is what we're doing. This is what the project for our generation is going to be. And that further energy is created by antagonism from rival schools. So you have different levels of disagreement in the system. You have these centralizers who are duking it out. But by having this kind of fractionation, what you get is a certain energy that creates a productive discourse that leads to kind of the golden eras of philosophy that we think about. And you can liken his idea of viewing philosophy in the shape of an hourglass, where what you have is you have these very fragmented discourses. You have this centralizer who takes all these different strands and they pull them together. And then from there, it kind of reinvigorates philosophy anew, like a phoenix. So what we did was Collins had 55 different networks in his book, and we just digitized all of them. So there's 55 networks. In them are 3,000 different philosophers or thinkers. These range from the pre-Socratics. There's an even older Hindu network in there, up to the Vienna Circle and kind of the origin of complex systems around John von Neumann and computation with Turing. These networks are all over the place. We have them in North America, all over in Europe, the Middle East, India, China, and Japan have a lot of networks. I know that in our map, there's only one dot, but actually there's many representative networks from all these places. And what we did was we took these very messy networks. This is the one with Newton, and we turned them into edge lists so that we could digitize them as such. And so we did that for all 55 networks, all 3,000 philosophers, and we did some work on them. So we collected 13 network measures, one cluster relating to centralization, how centralized is the network, and then one related to community structure, how many separate communities are there. And we had two levels of measurement. One is looking at the network as a whole. So you could basically do things like calculate the modularity of the network for the past 200 years, but also taking these generational, about 35-year time slices and calculating each of these measures for that. So instead of trying to calculate, say, Newton's centrality relative to Bacon, right, you could just calculate his centrality relative to Leibniz or others who lived during his time. What's important here is that each of these systems, each of these philosophical discourses can be characterized as being either extremely vital. These are instances when new ideas are emerging, old ideas are being killed. There's kind of a flurrying of philosophical activity in terms of the number of texts, or static. And in a static system, oftentimes, this is not a normative statement. Oftentimes, what is privileged is the holding of tradition. You don't want things to change. What the system is optimizing for is keeping everyone kind of on the same mark. And what we did is we tried to do a comparison between these vital systems and these static systems to see if anything fell out. So the first thing we did was a PCA, principal components analysis, where we took several of these network measures and we tried to see, can you distinguish between them, all these different variables? What we found is that on the first principal component, basically explains 74% of the variance. And as you add PC2, there's about 90% of the variance in the system. So in this plot, what you see is PC1 on the y-axis and PC2 on the x-axis. PC1 is related to centralization, how central is the most central person there, what's the path length of the system, and so on. And on the x-axis is subgrouping. How many different groups are there in the system? How many disparate communities? What's the modularity of the network? And what you find is that the vital networks and the static networks in this PC space do distinguish from one another, more so on the first principal component than on the second. So this cross here and the large dots is the community average for the static and the vital networks. What you find is that if you do a regression on this, what you find is you can predict pretty well from PC1 whether or not a community is going to be vital or it's going to be static. But PC2 really doesn't have that same power. So, but remember, that was for the whole network. And what we did is we wanted to look at how do these networks evolve or unfold over time. As you see, this is a temporal sequence going all the way from Galileo to Berkeley and even further. So we want to take this principal components analysis and we want to see how does it change through time? How is it that a system goes from being, say, low in PC1 or high in PC1 to low in PC1 or vice versa? So instead of looking at these principal components for the whole network, what we did is for each time chunk, we calculated it for each slice. So in the blue, these are your static networks, and in the orange, these are the vital ones. And what you find is that they immediately distinguish from each other right off the get-go, and there's a little bit more exploration in terms of what's happening in PC space for the vital ones over the static ones. So what's changed here is the y-axis is the cumulative network structure, which means that we are calculating how this PC changes, how these principal components change additively, such that you have chunk 1 plus chunk 2, chunk 1, 2 plus 3 plus 4. So it's kind of building the network over time. And on the x-axis is you're just looking at the cross sections. So how much are they distinguishing at each iterative time slice? So not only are they changing as a coherent whole in terms of their network arrangements, at each point in time, the vital networks are kind of altering where they were previously, such that 35 years ago, the discussion may have been, less centralized, but it's getting more centralized over time. And that speaks also for the whole network. So in terms of the in terms of the different measures that we took, we used a mixed effects model examining, say, looking at these different parameters. So things like how many communities are in the system based off of, what's the vitality of the system and is there interaction with time? And what you find is that on the x-axis, you see that's time. On the y-axis is the scaled number of communities in the system. So for the number of philosophers at each point of time, how many communities are there to represent them? What you find is that there's an interaction with creativity and time, but there is no interaction for creativity. So at the beginning, the vital and static networks are the same in terms of their community composition. But if you rebase the mixed effects model to basically look at the end, what you find is that they end up in very different spots, such that the static communities have fewer communities over time, while as the vital communities go through this compression event, where they decrease the number of communities such that the network is more centralized. You can also look at peak centrality. This is a measure of how central is the most central individual in the network at a given point in time. So, you could think that someone like Newton was very central for his time. Did the person who succeeded Newton, were they even more central than he was? And again, you find this effect where the networks are not distinguishing between vital and static at the beginning, but they're differentiating at the end, where what you end up with is even more centralization. You end up with even more kind of large figures in the vital network than in the static networks over time. Now, one thing we looked at was whether or not the philosophers in these systems agreed or disagreed with each other. So for each connection, for each edge in each network, they were weighted. So if they had a positive weight, that meant they agreed with each other. They were collaborators, for instance, or one was a master and one was a pupil. But if it was negatively weighted, that meant that the two had some kind of conflict. Because a lot of ideas regarding what increases innovation in a system say, well, if you increase the amount of disagreement through time, what you'll get is you'll get better outcomes. That increases the diversity as well. But what we find here is that both vital and static systems or types of communities, they start in the same place, they end in the same place. They're equally as disagreeable with one another. So even in a static system, it's not that everyone is agreeing on the same thing. But what's happening is they are structuring their disagreement different from one another. So bringing this back to the theoretical work that we discussed earlier in the talk, we can think again about, the role of these centralizing figures in terms of what they're doing. So on the y-axis, what you have is the normalized degree, or you could think how many connections does an individual have relative to others in their network of individual philosophers. And on the x-axis is the mean degree of their own network. And what you find is that some of the usual suspects stick out in the history of philosophy, even within their own networks. So John Stuart Mill was very important for his time. Husserl, founded modern phenomenology, so it seems that he was the most gatekeeping philosopher in our database. But Socrates, Confucius, Kant and Leibniz, all of these people end up being really important in terms of their centrality in the system. But also what you find is that if you look at vital and static communities and you look at, say, what was the centrality of the most central person in the system, of the second most central person in the system, the third most central person in the system, what you find is that the vital communities have just a few individuals um, who tend to be way more central above all the rest compared to the others. And then there's a steep drop off where the vital and static communities, their patterns effectively become the same, such that the fourth most central person in a vital community is going to be about as central as the first in a static community, and so on and so forth. So you have these kinds of tails, these individuals who show up, they construct the discourse, everyone's paying attention to what they're doing, what Randall Collins calls an attention space. And they're the ones that seem to be really shaping the community structure in the system. So going back to all of this, kind of a larger project that I think would be really important that we would like to do is examining meta-epistemology from this kind of lens. So right now we have a philosophy of science, we have a science of science, there's meta-philosophy, philosophers who study philosophy, and then we don't have this yet. And my hope is that this research and other kinds of stuff that I'm doing will be a nice step in the right direction in terms of taking our scientific lens and turning it back on kind of our parent to all the other disciplines, which tends to be philosophy. Because if you think about it, philosophical discourse and the things that we call philosophy tend to distinguish themselves from science in that they're purely communicative. There aren't experiments being done. This is just how discourse happens, whether in theory, whether in logic and philosophy and so on and so forth. And so trying to find the origins of this and some of the things that allow you to increase productivity or innovation in these discursive systems could be really helpful. And going back to where we were talking about earlier, the motivations behind why it's important to look at the individuals in these systems, who's really driving these things. As we go from phenomenological models to these mechanistic models, we might be able to ask different questions. So oftentimes the study of collective intelligence likes to inform us that, hey, by using this field, we'll get better forms of democracy, or we'll solve climate change and so on and so forth. But I think there are other kinds of questions that we can use to understand an individual's role in their own system. So I was really particularly influenced by this guy here, Joseph Ratzinger, Pope Benedict XVI. And in a conversation he had with Friedrich Hayek back in 1976, they were discussing what's really the role of the intellectual in society, like what kind of duties or values do they hold, or what should they be doing to improve things? And something he noted is he says, it's fine to have experts, giving their judgment on economics or on questions of political philosophy, but these really aren't human questions. Like, we've turned the human into a subject within a subject rather than asking questions about the human themselves. So, here was, for example, the assassination of the Archduke Franz Ferdinand, which was really, I think what set off the 20th century. And in particular, its primary crisis, which was a crisis of identity, where people were trying to understand what kind of system were they inside, what kinds of group did they belong to, and so on and so forth. And that's been the focus of a lot of the questions that have been asked in these kinds of social sciences, in anthropology, sociology, my own field of cognitive and information sciences. But I think what we're looking at now in the 21st century is a crisis of agency. So this on the right is the map of the internet by the Opti project, made in 2011. And it's highly centralized. You just see all these nodes, different websites, and so on and so forth. And you can only imagine that over time, this has only become more connected. And when I look at something like this, and you start thinking about, what is someone's role, or what can they actually do in a system that's so connected and dense like this? You start seeing chickens, on their way to the chicken nugget slot. So the questions that I think moving from a kind of phenomenological approach to a more causal mechanistic approach that you can ask about collective intelligences or, what is the role of the individual in the face of their increasingly faceless and automated world? Or how is it that humans as individuals can enact change? How can you measure agency within these larger social constructs that we find ourselves situated in? And for that, we're going to have to step back from these statistical models and try to understand this causal mechanistic. What's going on with the individuals within their larger systems? So right now I'm doing a lot of work, developing some things to understand this using partial information decomposition and information theory, trying to quantify things like social agency in light of these models, with the thought that eventually we'll be able to apply these to actual systems like voting or organizations, for example. So with that, uh, that's pretty much what I have. I really appreciate you all for inviting me. And these are my collaborators and kind of what I work on. And I'd be happy to take any questions.
Hi, Cody. Yeah. Thanks for the great talk. I
Thank
guess
you.
something this was kind of inspired by what you were saying at the end, and I don't know if this is like a good question per se, but I'm kind of interested how you think about like progress because you talked about kind of agency, right? But I mean, and this is kind of inspired by philosophy, right? So if you have this kind of network system and you're able to you're able to kind of identify discourse points, who does philosophical schools kind of influenced by, or who carries who are people responding to and then responding to and responding to and so on and so forth. But like, that all that does to me is it tells you a lot about discourse. But what about, again, progress, quote unquote, whatever, however you choose to interpret that.
Yeah, that's a great question. And one I've been struggling a lot, right? Because you can think about progress in terms of what are the action sets available to a person over time. Is it the case that GDP go up is progress, or is it the case that what you need to be looking for is are people able to self-actualize and do things that they want to do? I think in light of examining different systems, so I have kind of a flurry of projects, including, how do people gain traction on Twitter and so on and so forth, trying to examine these. And I think what's important is that you have to be able to treat each system as its own system in terms of what it's trying to maximize, such that we're not applying, say, the standards of collective problem solving that we saw in science piecemeal onto philosophy or onto voting systems, right? Eventually, what we want to be able to do is we want to be able to reverse engineer what a system is maximizing for just by looking at it. But in my view, the other thing that you can do, and this is kind of my motivation behind why I did the projects the way that I did, is I remember one time I was driving with a friend and he was a construction worker, and we drove by this site. I think they were building like a stadium or something like that, and he said to me, "Oh man, those guys really don't have their act together." And I thought it was really interesting because we couldn't tell what exactly they were building, but by merely looking at it, he was able to say they're still not doing it right. And so the question is are there going to be, diagnostics that we can use to understand, regardless of what the system is, whether or not what it's trying to do is doing it well? And so part of the motivation behind looking at philosophy is that its system of discourse underlies a lot of the structures that we see in science, that you see in like startup structures and things like that, and hoping that it transfers into these other more bespoke systems. And so, on the one hand, you can look at progress, but you can also measure something like epistemic health. Does it look like the system is healthy, even by its own standards, even if we don't know what it's trying to maximize for, right? Um, I might not know the goals of the system, but it may be possible to look in it and say whether or not it's behaving in a healthy way. And developing measures for that, I think, are going to be it's going to be very hard, but very important to do.
Yeah, that makes sense. Thank you.
Thank you.
Are there any other questions? All right, yeah, if not, yeah, thank you for your time, Cody.
Great. Thank you so much.